want to follow along, you can grab the Jupyter notebook at my GitHub link here. I'd highly suggest it. Everything's self-contained. I'm going to make this a little bit interactive, but we should really start at the beginning. So this talk is called Amusing Algorithms. What is, sorry.
I would love to follow along. Can you put that up?
Oh, sure, yeah.
A second longer.
You can just search Max Humber Amusing Algorithms. Does everyone have it? Okay, cool. So, start at the beginning. What is an algorithm? I found this tweet on my timeline a couple days ago. Thought it was pretty hilarious. An algorithm, noun, a word used by programmers when they do not want to explain what they did. Okay, what actually is an algorithm? Pulling from Wikipedia, you can see that it's a self-contained sequence of actions to be performed. That's a little bit nebulous, so let's drill down even further. An algorithm is just a step-by-step set of instructions that tells you how to do something. So this is the first thing that I found on Google Images. It's how to put a book in a box. Not sure why you'd want to do that. Not sure why it's the most popular image, but it basically tells you exactly what you need to do. Open the box, pick up the book, put the book inside the box, and then close the box. That's an algorithm. And if you run it every single time, you'll get the exact same result. Algorithms can be much more than that, though. It can be a recipe. So this is a recipe for sweet potato quesadillas that I made a couple nights ago. It's just a step-by-step set of instructions that will allow you to do something with inputs and generate predictable output. Algorithms can be something like a heuristic that allows you to translate from Celsius to Fahrenheit. So I come from Toronto in Canada. We play with Celsius. So the algorithm I learned was, hey, take the value, double it, and then add 32. That's how you get to Fahrenheit. And they can be things like machine learning algorithms. So KNN, classification, they can be linear regressions. Not going to touch on any of those because I found a couple of algorithms that I think are actually pretty interesting, amusing, if you will. So this was the abstract. This might be the first time that I'm going to deliver exactly what I promised. So we're going to use Jupyter. I'm going to give you a couple algorithms that will help you find love, hopefully. If you don't come after me. We're going to show you how to buy the best scalpers tickets at a baseball game, and an algorithm that will maybe prime you to think about when it might be time to leave your job. So the algorithms that we actually will look at are optimal stopping, stable marriage, and simulated Yawn. So with the preamble out of the way, let's just dive right in. Optimal stopping. I'm not going to read all this, I'll just paraphrase, but essentially the problem is this. It was imagined back in the 1950s. It was called the secretary problem, and it's, okay, you've got a stack of resumes, let's call it 100. You don't have time to interview every single candidate. What are you to do? So you basically have to sift through the resumes, call in a few different people, and find your secretary. A little bit old-fashioned, but the answer to this problem is actually just 37. To help us get there, I'm not going to use secretaries. Instead, I'm going to use baseball. I'm going to use the Blue Jays because that's my hometown. And again, from the preamble, I'm going to talk about scalpers tickets. So we're going to get to 37 from all of this. So when I go to a Blue Jays game, I live very close to the Sky Dome where the Blue Jays play. Games start at 7. I show up at around 7:30, and I like the cheap seats. So up here in the 500s or the upper bowl, you can essentially find tickets for between $8 to $24. Actually, this was last year. The Blue Jays are garbage this year, so tickets are even cheaper. But if I'm taking out a friend, we're going to show up at 7:30, and we need to find a scalper that will get us tickets for super cheap so we can go in, have some fun, and drink some beer. So let's say that there's 15 different scalpers, and in a perfect world, we'd know what each scalper is selling each ticket at, but of course we don't live in a perfect world. So let's imagine that one scalper is selling tickets in the 500s for $11, another for $24, another for $15, and $16, and $16. You can read the rest. And between different nights, even though I do this a bunch, I've developed a relationship with some of the scalpers, and they have different prices each night. It depends on where they're buying their tickets from. So it can be, I don't know, somewhat random. You might go to a scalper one night and they're selling tickets for $11. The next it's 18 or 19, all the way up to 50. So how is it that we can show up at 7:30, try to get into the baseball game within like 10 minutes, because I don't want to miss the full thing, and not go to every single scalper? I just want to find the best ticket, for the best price in the least amount of time. So I mentioned before I live right beside the Sky Dome. This is typically where the scalpers situate themselves. So there's around 15 different pockets denoted by the stars. I'll basically stroll up, ask a couple, and try to establish a benchmark. So again, let's take this set of options, or this list of options for now. I don't know what every single scalper is selling these tickets at, so I have to go around to each. So I'll start from the west side, and I'll make my way through and just ask, like, hey, what's up tonight? What are you selling tickets for? So here's the actual algorithm. I said 37%, but there's a little bit more to it. Essentially, if you want to find the best ticket for the best price in the least amount of time, you estimate how many possible options there are. So I know I've done this a couple different times. There's about 15 different scalpers. So I got to take that number, multiply it by 37%, and then evaluate that number of options to establish a benchmark. So in this case, it would be, if there's 15, take the first 5 scalpers, basically just figure out what they're selling them for, and don't make a decision until you've established a benchmark. So let's say I go to 5 different scalpers. I find that the benchmark tonight is like $11. I continue after the 5th scalper to go to the 6th, and if they're selling for $15, I say no, go to the next. If the next scalper is selling it for lower than the benchmark that was already set, you automatically pull the trigger. So let's take that pseudocode and break it up into Python. So this is the skip number, the benchmark, and we're essentially cycling through all the different options until we hit an option that is less than or equal to the benchmark. So I'll run this. See that, yep, the skip would be 5. And in this scenario where the options where the first scalper is selling the tickets for $11, then 24, then 15, then 16, then 16, my benchmark would be 11. I'd go to the next scalper at 17, say no, but the scalper after that at 10, I'd say yes automatically. And this would actually get me the best ticket in the set of options. I'm going to refactor a couple of different things, because although I ran the Python, like this still isn't super tangible. I want to make it a little bit more concrete. So I'll refactor it by simplifying the algorithm with a break in the loop, create a function that will give me different options. So if I'm taking my dad out and I want to impress him, I'm not going to bring him to the cheap seats. I'm going to maybe splurge and get tickets in the lower bowl from 60 to 100. Maybe there's only 10 scalpers per night. So we can run that. And then refactor the algorithm to show you in contrast about what you might do if you don't follow this optimal solution. So there are 2 different strategies that I put in here. First, so just buy the ticket that the first scalper is selling, or go to a random scalper and buy their ticket. So we can see that when we wrap all this into a buy function, and then return 1 if the choice actually was the min of all the options, we can take this and then simulate. So if I were to go to 1,000 different Blue Jays games and use the optimal strategy with ticket prices between $8 and $24 in the 500s, there's 15 scalpers, run it 1,000 times, 49.3% of the time, I'd be getting the best ticket price. If instead I just went to the first scalper and bought the first ticket, I'd be getting the best ticket price 9.3% of the time. And then random, it would be 8.9%. Again, like this is, you can keep running them through. It's not going to be perfect. It's around 10% because there's how the tickets are laid out. So I think this is pretty cool. It's an algorithm that can be applied to many different facets. One that I've actually been using in Toronto is I'm looking for a new apartment. And I've taken this algorithm and I've said, hey, if I'm going to go to a new apartment, I've got 10 different options. I'll go to the first 3, check them out, non-committally, and then as soon as I find an apartment that is better than that set of 10, or better than the set of, I guess it would be 4, I immediately pull the trigger. So this is all you need to remember. I think it's super useful, super fun, and now we can move on to stable marriage.
Switch this real quick, because the video's not recording that.
Oh, no. You guys can all hear me? Yeah, okay. So you can read this yourself, pick it up from the Jupyter notebook as well. But essentially all this is saying is, imagine you have a pool of men and a pool of women. Each of them have preferences. And you're trying to match them up such that everyone is going to be happy. Everyone's going to be in a stable union such that no one wants to break that union and go to someone different. I find that it's super easy to explain this algorithm with people that we know. So you can take someone like Ross, Chandler, Joey, Rachel, Phoebe, and Monica, and you might fight me on these preferences, but I think they're kind of accurate. You can see that like Ross really likes Rachel, then Phoebe, then Monica, Monica being last, otherwise it'd be incest. Rachel really likes Joey, then Ross, then Chandler. Again, so given this set, how can we pair up people such that everyone's going to be stable, everyone's going to be happy, and we can move forward? In order to get to the algorithm first, we need to define a data structure. So this is just a class called person. So you can put in someone's name, their preferences as a list, and then this is just a string representation. So if they are partnered, you'll see this union here. If not, it'll be open. So Ross, for example, would look like this. And you can see that, okay, when you initialize Ross, he will have no partner, and so he will display like this.
But do you have another data constraint? It's Monica and lots of brothers, sisters.
That's a good point. Do I have another data constraint? No, not for this. Maybe I could embed it later. But yeah, when Ross is partnered up with Rachel, this is what the data structure is going to look like. We then need to give each of these people a role. This is going to be a little bit old-fashioned to start, but imagine that the men can do the asking, and the women can either do the accepting or rejecting. So I'm going to subclass person into different roles called alpha and beta. So alpha is doing the asking. These have these ask functions, so it essentially takes the list of preferences and then pops off the top, asks that person, and then for the beta, they can do the accepting or rejecting. They take the suitor, so if it's Rachel, Ross is second on her list. She would basically return true if she does not have a partner, or true if the suitor that is presently courting her is earlier up in the list than her present partner. So with the preferences defined as a dictionary, this is just from the picture before, we can seed and initialize everything. So I'm grabbing from the dictionary all the men, stuffing them into alphas, grabbing all the women, stuffing them into the role of betas, and then printing up the setup. So you can see Ross, Chandler, Joey, all unpaired. So here's the algorithm. Basically what you have to do is you have to take all the unengaged men and then basically take a random one of them, and then he proposed to the woman that he prefers most. That woman will automatically say yes or maybe because she has no other options. But essentially you keep running through this loop until all the men are engaged. This is what the Python looks like. So I'll run this and then print out the matchings. So you've got Ross is paired to Rachel, Chandler is paired to Monica, Joey's paired to Phoebe. But wait, like, that was a little too quick. And in fact, if I just give you this, it's not, like, I can't understand this. Like, sure, it's Python, I can maybe understand the Python code. Let's slow things down and actually pick apart and see what this algorithm is actually doing. So this is the original algorithm. And I'll just explode it with a couple different print statements and some sleepers. So we can exactly see what's happening at each moment inside the loop, so to better understand what is going on here. So let me shrink this a little bit, run the loop. So you can see Chandler asks Rachel, Rachel accepts. Joey asks Phoebe, Phoebe accepts. Ross asks Rachel, Rachel accepts, but she was already paired, so she has to jump Chandler. Chandler goes back into the pool, and then Chandler asks Monica finally. So everyone is paired up, things are stable, and that's the algorithm. That's not super amusing though. So you can print out the pairings. Let me increase the font size. And see that, okay, Ross got his first choice. Chandler got his second choice. Joey got his first. But the women all get their second, third, and second choice. So what's super neat about this algorithm is when you start, everyone has a preference. And when the men go first, they assume the role of the alpha and they do the asking. Here are the outcomes. When you reverse the roles and have the women be the alphas, do the asking, and the men do the accepting and rejecting, you can run the algorithm. I won't do the print statements this time. But you print out the pairings, and they're entirely different. So both are stable, but the women this time get their first, and second options, and then the men get their second, and second options. So before, men basically got all their first options. How could this be? So when you look, this was the picture when the men went first. This is a picture when the women went first. And it's essentially the difference between, if you're doing the asking, you are going to get the option that is the best option that will have you. But when you're just sitting around and waiting for someone to come up to you and you're doing the evaluating, instead of getting the best option that will have you, you're getting the least worst option. So you can kind of wrap this up, and I've chosen a couple different quotes that I think capture this quite nicely. It's, pearls don't lie on the seashore. If you want one, you must dive for it. And then opportunity dances with those on the dance floor. So if you're in a bar with a bunch of different buddies and you're just waiting around for someone to come up and talk to you, you are getting the least worst option. But if you're a little bit regressive and you actually put yourself out there, you're getting the best option that will have you. I think that's pretty powerful. With stable marriage out of the way, let's get to simulated annealing. So I just recently learned this about a month ago, where if you watch a show like Game of Thrones or any like medieval show, you'll see them making swords, and they'll put the sword in the fire and they'll take it out, and it's basically shaped, but they keep hammering it. Like, why do you keep hammering a sword? Well, it's called annealing. And some of the reasons you might want to anneal a sword is because it reduces hardness, it increases toughness, and decreases brittleness. So if you don't take the sword out of the fire and keep hammering it, essentially you'd use that sword and it would just automatically shatter. That's because when the sword is cooling, all of the molecules are finding themselves into states that might be suboptimal. So you need to hit the sword with a hammer so the energy or the atoms are excited out of their suboptimal state into maybe something a little bit more high energy in the hopes that they're going to settle down and become a little bit more stable. So instead of talking about swords, you can maybe make this a little bit easier to understand and talk about a mountain. So imagine it's super foggy outside and you want to climb a mountain. So you want to get to the very top. But if your algorithm is look left, look right, go up, and you keep doing that, you might find yourself on top of a local maximum instead of the peak, because you might find yourself on top of the peak and you've got nowhere else to go. So a better algorithm is to take the things that we've learned from making swords and simulate the annealing process such that we can like bounce around and actually find the global peak, or get out of a local maximum. So in order to show you the Python, I've got to set a few things up. I wanted to do this in pure Python instead of using NumPy, so I'm not sure why. Just thought it'd be fun. So I have a couple of convenience functions, and then the function that will simulate like a mountain or a hill or a range, and you can see what that looks like. So here's my mountain range, and depending on where I start, if I use the hill climb algorithm and I start at 4, I go look left, look right, go up, look left, go right, go look right, go up. If I start at 4, I'd end up on this peak. If I start at 5, I'd end up at this one. Still, none would get to the very top. So you can see that by printing the functions in this way. So at 4, your y value would be 6.3. At 5, your y value would be 1. And again, you're kind of finding yourself through this mountain range and finding yourself on top of a local peak. So the hill climb algorithm that I described can be represented in an if statement like this. And I can wrap it up in a function called hill climb and basically print out, okay, if I find myself at x value 4, I climb up the hill and I'm going to reach a peak of 13. If instead I start at 5, I'll find myself at the peak at 17, but still it's not the global peak. So I'll show you again what that looks like. So yeah, you start here, you end up there. You start here, you end up there. How can we borrow from sword making, integrate simulated annealing such that we find ourselves on top of this peak over here? So I think that there's a parallel in climbing a mountain to perhaps your career ladder. If you are just following the path of least resistance and doing the safe thing, just getting promoted year after year within your same company, I think you're going to find yourself on top of a local peak. It might not be the best option. So with simulated annealing, it's kind of taking a chance. It's injecting randomness, moving yourself to a place that might be suboptimal in the hopes that if you keep on doing the hill climbing algorithm, you'll eventually get to the very top. So here's the pseudocode. I'm running a little bit at a time, so I'm going to skip over that and just give you the Python, the good stuff. So essentially what we need to do in the pseudocode, there's this function here that basically generates a probability of acceptance. So it basically takes the energy for your old point and the energy for a new point, and then a temperature that decreases over time, and spits out kind of a random chance of whether or not you're going to accept that movement. So here's the function that does that, and I'll show you how this works. So if your old point was at 10 and your new point is at 9, again, remember we're trying to climb up a hill. If you run the acceptance probability with these varying temperatures, so if temperature is 10 or temperature is 1, then you can see that, okay, at higher temperatures, we're just going to accept. At lower, we're not. And if you increase things to something ridiculous, like, okay, if your old point was 15, your new point is 9, then the probabilities that you will accept that will decrease. Here's how the temperature will decay. So you take an alpha value, chosen something a bit conservative. This is how the temperature will decay over time. And then this is the actual algorithm. So it's the pseudocode from before. We're taking this probability of acceptance function and then basically flipping a coin against it. And if it's greater than or equal to, we're going to accept. So toss the new value into the current value and then decay the temperature by this alpha value I've defined here. So if we start at 4 and decay at 90%, you'll find that, can't really see that, but essentially we're going to find ourselves at an x value of 9. So that's not super interesting, and again, like I want to make this more tangible, more interesting, and a little bit less nebulous. And the way that I've found you can do that is, again, with graphs. So I showed you from before the hill climbing bits. I wanted to create a GIF and animate what the simulating annealing function was actually doing. So I'm breaking my rule, and the only non-standard libraries that I've been using in this presentation are matplotlib and then image.io. Matplotlib does have some extensions for animating. I just find them super clunky. I really like image.io because it's extensible, you can use it with anything, and I've been playing around with it with Altair as well. So if you generate the images and just stack them on top of each other, image.io can create a really nice GIF. So here is the entire flow, the entire algorithm, and I'm just saving the values at each point. So I'm saving the x values into a list called x, saving the y values into a list called y, and then the temperature at each moment in time. You can see that, okay, I'm going to have 100 different steps. And then when I use, or rather when I loop through matplotlib for each of the different lists, so for each of the different steps in the range of all of the lists, oops, I can basically generate a bunch of different images. So this is going to take like 25 seconds. So we're generating a bunch of different images. Once the asterisk clears, we'll know that it's worked. Nearly there. There we go. I can then take all the different files, move them in, sort them by integer, and then use image.io to append things to this image list, and then save it to a GIF. So I'll have the duration between each frame set to 10 milliseconds. I'll run that. Again, this is another 25 seconds. Do a little cleanup. And then show you the GIF. So this is simulated annealing in action. You can see that it seems a little bit random at first, but as the temperature decreases, the probability that you actually move around and get shaken away dramatically decreases. So whereas we started at 4, we bumped around, and now we're finding ourselves not at the peak over here, or the peak over here, but closer to the global maximum. So using a GIF, animating matplotlib images in this way, I think really helped me better understand what was going on with simulated annealing. And you can effectively codify that in a little statement here and just say, like, hey, in an impossibly complex world, we perhaps should shun temporary stability and instead be willing to tolerate a bit of volatility in order to find a greater stability thereafter. I think there's a lot of power in that, because if you do just follow the path of least resistance, if your algorithm is hill climb, you might not be finding yourself on top of that global peak. So the way that you can think about temperature is, as you're younger, you're full of energy. You've got a very high temperature. As you age, your temperature might decrease, and so you're not going to be taking these crazy risks and move yourself around on top of this map. So I like to take this algorithm, think about it in different facets of my life. Right now I'm thinking about it for my career. But that's essentially the presentation. I just came up with the Python implementations of these algorithms. I wish I was smart enough to come up with the algorithms themselves. But I found each algorithm in each of these books, so I highly recommend that you pick up each. This Idea is Brilliant, which is published from edge.org. The Mathematics of Love, which I grabbed the stable marriage problem from. And then Algorithms to Live By, which was the very first. And then if you will, or if you will allow me, I actually just published a book, so you can check it out on Amazon. If you want to come up to me afterwards, I'm actually looking for reviewers. So if you give me your email, I can hook you up with a review copy. And APress just essentially needs people to build up my Amazon cred. So that's it. Here I am. I hope you enjoyed it. This was fun. Thank you.